All right. So what we're going to do here, this is the module 3. It's called Energy Bands and Carriers in the textbook, but the way that we can think about this module 3 is that we've covered in module 2, we've talked about how electrons are arranged in individual atoms, and now what we're going to talk about is how electrons are arranged in solids. Okay. We never work with a single silicon atom in practice, right? It's always a lattice of silicon atoms. So the reason we started with the individual hydrogen atom and then, individual atoms, and then we talked a little bit about the individual silicon atom was because those were simpler problems. They allowed us to gain an intuition of the Schrodinger equation. They allowed us to give an intuition of electronic configurations. But now we're going to talk about how they're arranged in solids. And the key difference is discrete energy levels versus energy bands. So with individual atoms, there was the 1s energy state, the 2s energy state, the 2p energy states, and so forth. They were discrete energy states. They were very specific energies that each one of those states had. And as part of your homework, you guys are going to calculate, with a simple example of the Schrodinger equation where you calculate the eigenfunctions or the solutions of the 1D potential well. And for each one of those solutions, there is a corresponding energy that you can calculate. Similarly, in the hydrogen atom, for each one of those wave functions, there's an equation for the energy that you can calculate. Okay? So they were discrete energy states. What happens in solids is that these discrete energy states become energy bands. An energy band is a continuous range of energies, and the electron can reside in any one of those energy states within that range, rather than at discrete states. So we're going to talk about that. We're going to talk about mechanisms of current flow, how to calculate carrier concentrations in semiconductors, and how to calculate electrical currents in semiconductors. So the practical example that you should be able to do at the end is, if I give you a resistor, if I tell you I have a semiconductor and this is the doping level, and what's the resistance of this material? Okay. So in some ways, we're thinking about the simplest type of electronic element, which is just a resistor. And so if you want to think about how do we build stuff, this module will talk about how do we make a semiconductor resistor. Next, the future module will talk about diodes and MOSFETs and bipolars. So with this module, just like before, I'm combining stuff from a few different textbooks, a Streetman book, which is the main textbook for this class, but also the Niemann Semiconductor Physics and Devices. There's this Dmitriev book, which you've probably seen a few figures from there, and then the Crane Modern Physics, which is the book that I hyped up last time. All right, so we're going to talk about the electronic configuration of covalently bonded silicon. So let's first talk about the single silicon atom. So with the single silicon atom, you had these electronic configurations. We just did that, and this is what it looks like. You had the electrons filling up these states, the 3s state, and then the 2 electrons in the 3p state. So this was the electronic configuration that we just did at the end of last module. The way the chemists draw this is that they say silicon has 4 electrons in its outer shell. And what they're referring to here is, to connect the concepts, is that there are 4 electrons in the outer energy level, so the last n value. So with silicon, it's n equals 3 is where the outer electrons happen to be. And there's a total of 4 electrons in the outer shell. Okay, so we also talked about in module 0, when we talked about crystal lattices, we said silicon forms bonds with 4 other silicon atoms around it. So this electron here, each of the electrons around the silicon atom forms a bond with 4 other silicon atoms around it. So, there was a silicon atom here that had 4 dots, silicon atom here with 4 dots. On all sides. And this electron and this electron forms a covalent bond. This forms a covalent bond. This forms a covalent bond. And this forms a covalent bond. So we talked about the tetrahedral bonding, and what we're doing now is we're just looking at what the electronic configuration is of the same thing. So we're looking at it more in terms of what the electrons are doing. So the single silicon atom, the electronic configuration looks like this. It goes through a transitional state. You don't need to know this, but the lower energy states stay the same, and then the electrons reconfigure themselves into where you have a 3s, 3p, 3py, 3pz, but there's only one electron in each one of the shells. And then eventually it goes into this state, which is the state of covalently bonded silicon. The inner electrons are the same thing as before, nothing interesting happening there. But the outer electrons form what's called an sp3 hybrid orbital. All right. And just to connect this to module 0, when we said there's this tetrahedral bonding, that tetrahedral bonding, the bonding orbital, so the fact that these two electrons are shared between the two silicon atoms, when you have a pair of electrons forming a covalent bond, that covalent bond is represented by a hybrid orbital. All right? So each silicon atom in the middle it's bonded to 4 other silicon atoms covalently, and so there's 4 corresponding sp3 hybrid orbitals. And how many electrons are going to be in there? You guess? 8. Yeah, they're all going to be filled, right? So the way that we can think about this is that there are 4 electrons that are shown in black here. The black arrows are coming from the center silicon atom. And then there's also 1 electron from each of the neighboring silicon atoms that's contributing a single electron to those here. So, these colored arrows are there to show you that each one, there's 1 electron coming from the silicon atom on top. So there's a green arrow there, and so forth with the other ones. So each one of these sp3 hybrid orbitals represents one of the covalent bonds that's connecting the silicon atom to a neighboring one. Now, these are what the hybrid orbitals actually look like, what the shape of them look like. By the way, the shape, of course, we get the shape by solving the Schrodinger wave equation. We solve the Schrodinger wave equation with a different electrostatic potential boundary condition. So think about this for a second. How is the electrostatic potential boundary condition going to be different in the case of a lattice versus a single atom? I'm not looking for a mathematical answer. Just qualitatively, how's it going to be different?
There's going to be way more points of potential next to each other.
Yeah, exactly. There's going to be many more points of high potential, right? Each nucleus is a point where there's a lot of potential there. And by the way, like when I say high potential, I'm talking about high magnitude, right? The sign for potential is negative in the diagrams that we're drawing, right? So just keep that in mind. But the magnitude is larger because we have all these protons, and that there's an attractive force between the protons and the nucleus. So now we have a bunch of those nuclei scattered around. So your potential functions are going to look very different. We'll talk about that in the next slide. But because of that, when the potential functions change, the solutions to the Schrodinger equation also changes. And you can find out what the shapes of what the electron clouds look like by solving the Schrodinger equation and then finding out the probability densities and so forth, like we did before. We're not going to do that here. This is obviously a much more complicated problem. But this is what they look like in a single silicon atom here. This was the S shell, the 2p subshell. I said this is 3. We're talking about the 3s subshell. And then this is the 3px, the 3py, and the 3pz. Remember I said how the p subshells are mutually perpendicular. One is aligned to the x-axis, one is aligned to the y-axis, and one is aligned to the z-axis. So this is what they look like. They're like dumbbells. And you see that there's a positive and negative. I think that represents the electrons of different spin. And so what happens is that these orbitals, they combine to look like something like this. They form the sp3 hybrid orbitals. And notice that there is one on top, and these are no longer aligned to the X, Y, and Z axes. These are aligned to the tetrahedral lines that we talked about last time. So it looks kind of like a tripod, remember? Does anyone remember what the angle is between these orbitals?
109.5.
109.5, that's right. This is that classic tetrahedral bonding. The maximum, if you wanted to spread those electron clouds as far apart as possible, you put them 109.5 degrees apart. Right, so this is that tripod-like tetrahedral configuration. That's what the electron clouds look like. And when you draw them together as a set, this is what it looks like. All right, so each one of these clouds has 2 electrons, as I showed you on the previous slide, and that's forming a bond between this this silicon atom and the neighboring silicon atom. So let's talk a little bit about, like, we're not going to do solutions to the Schrodinger equation on this, but we're going to I want you to get a general qualitative idea of what's happening here. This was the probability density function of a single hydrogen atom. All right? So qualitatively, what was happening here is that the electrons, they had a certain probability of being at a distance. There's a high probability that they were at a distance roughly approximately equal to the Bohr radius. All right? This was for a single atom. So the farther away you go from the nucleus, there's a smaller and smaller probability that you'll find an electron there. So the electron is most likely to be fairly close to the nucleus, like this, near A0. All right? Now what we're going to do is we're going to take 2, so this was, this is the nucleus, and then you had the electron around the nucleus here. Now what's going to happen is we are going to take so this is a nucleus, this is a nucleus, and each one of these, let's say we take 2 nucleuses and there's an electron orbiting it, and we start bringing those nuclei closer and closer together. We can't actually do this easily in real life, but it's more of a thought experiment. So as we bring those nuclei together, what's going to happen is that these probability functions, this is coming from the wave function. Remember, like this is coming from the wave function squared. That's what these probabilities are. So these probabilities start to overlap with one another when you bring them together. Okay. So when these probability density functions start to overlap, this before, the electrons could only be in a very specific energy state that was defined by the Schrodinger equation. And if you solve the Schrodinger equation again for this type of boundary condition where you have 2 nuclei, you have 2 potential generating areas, then the solution that you get looks something like this, where there's 2 possible energy states, but they're very close together. So this is referred to as like splitting energy levels. Another way to look at this is shown here. So this is where we're trying to think about bonding in terms of wave functions. The book refers to this as linear combinations of orbitals. So what's different from this slide versus the previous slide is in this slide, it's actually showing the wave functions here, and it's showing the potential fields here. I'm going to make this a little bit larger so it's easier for you to see. All right. So let's start here. Remember before, if I put R here, and then I was plotting V of R, the potential field looked like this for a single atom. The potential field goes towards a very very large negative potential in the middle because you have all those protons in the nucleus. So that's what the lowest energy state is. Okay, so this is showing a V of R again. Now this, I'm going to draw this out here. Wherever I'm showing in red here, this is for the potential function for a single atom. All right, so this is the same thing here that I've shown here. That's for a single atom. When you start bringing two atoms close to each other, when you start bringing two atoms close to each other, then these potential fields actually superimpose on each other. They can actually add up. That's why they call them linear combinations. Okay, so if you were to add up the potential function of one nuclei, and you add another nuclei to it, add the potential function of another nuclei, the combined function that you would get would look like what's in black here. So this, and this. So your potential field that you plug into the Schrodinger equation now looks like this, right? Instead of just the two, the single atom potential field that you saw earlier. As a result of that, when you solve the Schrodinger equation, then, when you solve the Schrodinger equation, you get these two energy states. But let's look at it, also try to get another piece of intuition here. If you solve the Schrodinger equation for a one atom, an individual atom, this is exactly the thing that we did just 15 or 20 minutes ago, when we said there's an exponential decay. The further you go away from the nucleus, the probability of finding an electron drops. So that's what we're talking about with this function here. The psi function is large, and then it drops as you go further away. So that's for a single atom. And when you bring two atoms close together, the two psi functions start to overlap, and they can also be added. They call this a linear combination of orbitals. And what happens is that these wave functions can add. So if psi1 and psi2, if they add to each other, they form this bonding orbital. Okay. So if you add this function and this function, then you get something that looks like this. And what you notice here is that there's a high probability. The psi function is large when near the nucleus here, and there's also large near the nucleus here. But there's also a non-zero probability that the electron resides somewhere in the middle. That is the fact that there's a probability connecting the two nuclei together. That's the bonding, right? So this is what's called a bonding orbital. And if these two functions subtract, psi1 and psi2, if they subtract from one another, then you get a function that looks like this. And this is called an anti-bonding orbital. And that does not contribute to the stability of the bond. This is the orbital that contributes to the stability of the bond. So notice that the bonding orbital has a lower energy state, and the anti-bonding one has a higher energy state. So this also talks about energy band splitting when you bring the two atoms close together. Just different ways of thinking about it.
So for the anti-bonding orbital, is that when the electron configuration has to reconfigure itself then?
Well, I'm not sure what you mean by reconfigure.
So, so if you go back a couple slides, we're seeing the direction of the spins.
This one?
Well, even farther.
Oh, this slide here.
Yeah.
Oops. There we go.
So is that where we're seeing this hybrid actually, this covalent bond diamond glass actually change the direction of the spins?
I don't think it has to do with the changing the changing of the spins. It's just like which of these orbital states is a higher versus a lower energy. I don't know if I'm answering your question. Okay, we'll talk about it after class. I don't know. Okay, we'll finish up here and we can continue on this next time. So the key thing to understand in this module is that the band structure changes. The energy states change. All right. There's two major things to point out on this slide. This is what the energy band diagram looks like for a single silicon atom. We did that earlier. We drew out where all the electrons were. All right. Increasing energy on the y-axis. So notice that there's a finite number of states here. Okay. Because a silicon atom only has a certain number of solutions to the Schrodinger equation and a certain number of electrons. Here, there's many atoms and many states, and what happens is that due to the splitting of the energy states, you get a whole bunch of energy states that are clustered together like this, and that into something called the valence band, and another group of energy states that's clustered together in something called the conduction band. We'll talk more in details about that, but I just want to mention some brief things now, is that there's an energy gap between them, and this is called the band gap. This band structure of a material determines a lot of the properties. It determines whether a material is a semiconductor, whether it's an insulator, or whether it's a metal or a conductor. And then there's these inner states as well. So notice that a couple things to point out here. First of all, you notice that I've just drawn a bunch of lines here, okay? A bunch of lines corresponds to a lot of energy states. So when you, of course, if you have a lot of atoms, there's going to be a lot of energy states. The energy band diagram shows how those energy states are arranged. There's a whole bunch of energy states that are close to one another in a region that's called the valence band, and a whole bunch of energy states close to each other in a region that's called the conduction band. And then there so happens to be a region in the middle between the two. For silicon, it's about 1.1 electron volts, where there are no energy states, and that's what determines a lot of the properties. So we're coming to the end here. I don't think we have time to really talk about this, but just to give you a preview of what we'll talk about next time is we'll talk about a little bit about where this band structure originates from. You know, like the fact that individual atoms have these discrete energy states, but in a solid material you have energy bands instead of discrete states. And then we'll talk about energy band diagrams and how, where we come up with this energy band notation, what's a conduction valence band. And then we'll start getting into things like the mechanism of electrical current, doping in semiconductors, and so forth. So we'll end there. Please do give a chance on the homework problems, because next week, I would like to post the solutions by the end of this week and the weekend, and next week another homework set will be posted. So don't fall behind, because there's a lot of concepts to cover. Everything that we've done before will help you understand what we're doing in the future here. All right. Thanks everyone, and please email me if you have any questions on the homework.